continue with today's topic. Give me a second here. Right. So where we've done a lot. So now let's look at this last topic here, which has to do with question 5 and a variation of the Bode plots for two-pole systems. And this particular one, you're given, which is a variation of what the type of questions that you can be asked. You're given this information here. So here is a Bode plot or frequency response plot for a second order system. And the top diagram, of course, the Bode plot, we remember the Bode plot gives you two plots. One is a magnitude plot and the other one is a phase. Typically, what you were asked was to be, you would be given usually the normal type of questions, right? One variation of this is that you're given the transfer function, some G of S over HS. And then from that, you put it into a standard form. And then you use a series of straight lines to plot the frequency response of both the numerator and denominator polynomials, right? That is the conventional way, and for a lot of the systems that we do, that behavior works. There is one sort of exception, and that has to do with with certain types of second order systems. And we went through that before. That's there, and I'll go to the slides in a second. That a normal second order system is fine if the poles are simple, right? So simple poles, right? Simple poles, remember this is sigma j omega, this is the S plane. Simple poles means that the poles are on the sigma axis. There's no imaginary component. From the time you start to get a pole for a second order system that has an imaginary part in it, it means that the time response of the system now has a decaying or expanding exponent. And depending on where the pole lies, it may even have a cosine or a sine in the time behavior. All right. So let's go on and see what that does to us in terms of the frequency response and how we plot out the frequency response for those types of systems. Right, which is lecture 22. Remember, there were 3 lectures on the Bode plots. The first lecture dealt with the simple first order systems and so on. And you expected to know that our first order 0, the frequency response increases by 20 dB per decade, that our first order pole, the frequency response decreases by 20 dB per decade, a second order 40, a third order 60, and so on, right? So we were, when we did second order equations with complex poles, you know, we had a full lecture on that. And we were looking specifically at the general response. But what we saw is that if you were to find, given a system like this, if you were to find HT, right, depending on the value of zeta, this answer would either have a e to the, e to the plus or minus AT in the answer, or a e to the plus or minus j AT, that kind of thing, which led to a sine or a cosine, right? That's lecture 12 or 13, somewhere around there. And we saw the time responses for that a normal second order system, the step response, what you do is that if you put a step input for the system, a unit step, that the response for this, what you expect is that the system would give you this kind of response normally. All first order systems give you that. The second order systems we saw now, depending on this thing called a damping factor, you could get this behavior, or it could start to do this, or it could do it so much that the thing that oscillates and gets unstable all the time. And this behavior, this oscillation behavior, was directly related to this thing called a damping. Right? And one way I try to visualize it too is, for instance, the suspension in a car. The suspension in a car has a spring in it, but it also has something called a damper or a shock absorber. If that isn't working, then every time you go over a hump, the car is going to keep bouncing up and down for a very long time until it settles. So what the damper does is that it absorbs that vibration and tries to make the car settle down after a while. So like you hit a bump, that would be the equivalent of the step response for the car. And this purple is how the car would respond. The better the damper, or how it absorbs those sort of oscillations, is the more the closer it will get to this kind of thing. And we saw the damping factor in that same lecture, lecture 12 or 13, we spoke about underdamped, overdamped, and critically damped. Right? Critically damped was the one that gave you the response almost like a first order system. Underdamped was the one where it didn't have enough to absorb the oscillation, so it's doing this. And overdamped means that you have too much, so instead of responding like this, it's taking a long time to eventually settle down. All right? You probably want to, and this is where your controls will, systems, when you're doing that, will tell you, you probably, if you have to make a choice, you want to be in the critically to overdamped part rather than underdamped, right? Because a lot of systems would not tolerate, what do you call it, oscillations, and when you make a change, and we made that remark on Wednesday as well, that if you think about like a crane or a robot with a lot of mass on it, if it moves from one point to another, what you don't want it to do is, if it's going from point A to point B, that it passes, just think about it. If you have something in point A and you want to move it to point B, you wouldn't want it picking it up, right? And then it moves to point A, point B, but it overshoots and then it comes back and then it eventually settles down before it reaches point B, right? That is dangerous. So what you would want it to do is to move from point A to point B, and then it slowly settles down right here, which is this kind of behavior, right? So that is in the time domain and a sort of physical understanding of how the system behaves. So let's see what that does now in the, if you look at it in the frequency response domain. So you have a transfer function, and this was the second order, the general transfer function where the poles are complex, right? I said, if you require, check lecture, somewhere around lecture 12, 13, somewhere in that vicinity, 11, 12, 13. So somewhere around there, you will check it. It's for the responsive systems, first and second order systems. So if I give you a transfer function, it doesn't matter what it looks like, and I tell you what is the frequency response of that, the first thing you have to do is to make this substitution S equal to j omega. All right, and once you do that, of course, you get now this into this form. Remember, at this point, zeta has to be between 0 and 1. We derived why that would be, okay? In order to for the poles, we had substituted some poles, some values for damping in those slides, and you could and actually plotted what the responses were looking like. So we have it in the frequency domain, and now we want to, of course, before I do that, if I were to give you a normal second order system, what you would do, you know, this straight line plot for the second order system, if it has a second order pole, the frequency response would go to some omega 0 and decrease at minus 40 dB per decade, right? This would be the magnitude of the response, right? Remember that it's a second order system. So as frequency goes up, after the corner frequency, the response is supposed to decrease at 40 dB per decade. So let's rearrange. You remember, we like to get it into a form that we could sort of plot the frequency response. So what we do from here to here is that we divide everything through by omega 0 squared to kind of get the behavior. Look at, I divide through by this, and I get it into a form looking like this now. What is the magnitude of this? And it's really just should have had a magnitude sign here. The magnitude of a complex number is just, of course, the square root of the real and the imaginary part squared, right? So the magnitude response of this second order system will be something looking like that. How does that work now? Let's see if we could sketch it out. And remember, the whole thing with the Bode plots is not that I'm going to put in values of omega and see what happens. What I'm going to do is to see if omega is close to 0, if omega is close to infinity, what sort of behavior, and use straight lines to sort of flesh it out, right? Feel free to interrupt at any time too, right? I'm not, I have a second monitor here. I should be able to see the chart, all right? But better fit if you kind of yell out and say something, okay, if it's not clear. So when the frequency is low, right, close to 0, or if you remember, if omega is much less than omega 0, right? In other words, this bit falls out, this bit falls out. So what you're left with is A over 1, right? And if you convert that to decibels, right, this is going to give you the 20 log A minus 20 log 1, which of course is 0. So you get 20 log A. All right. And when everybody following that, right? You remember that was how we derived it. This was the lecture, the Bode lecture number 1, right? The first time when we were speaking about those plots, right? Now when omega starts to get very big, or it goes to infinity, or if you like, omega much greater than omega 0, right? When omega is much greater than omega 0, then what happens now? Okay, this is unaffected, right? When omega is much greater than omega 0, notice these two components we have in here. Let me just change the color a second here. I don't want to erase anything here. Notice this factor here is basically omega over omega naught to the power 4. Right? You could forget the one for the time being, but you have an omega over omega naught to the power 4. Here we have an omega over omega naught to the power 2 squared. So this, as omega gets very large, this dominates this. Yeah? Fair enough? As it starts to get big, because this is a factor of to the power 4 as compared to a factor of the power 2, this will dominate this. And if you look at it as well too, inside of here, right, if I expand that, I am going to get, right, another thing like, if I were to expand that, I was going to get something like a minus 2 omega squared over omega naught squared inside of that bracket, if I were to open up everything, right? So that, by the time you square this on this side, right? If you square that, you're going to have 4 minus 4 because of the j squared, zeta squared omega squared over omega naught squared. Zeta is less than 1, so it's a fraction, all right? So that this whole bit 2 will be significantly less than this thing that we had here. And this in turn is significantly less than the omega to the power 4 over omega naught to the power 4. Yeah? Everybody seeing that? As omega gets very big, imagine omega being a very large number. So what it's boiling down to now is that what you're left with is a over 1. So forget this bit here. You're going to be left with a over 1 minus omega naught squared when you take the square root. And you convert it to decibels now, we get a 20 log a, and you have the minus 20 log omega over omega naught, which is, this is minus 40 log omega over omega naught, right? So in other words, well, this is a straight line here. This now is decreasing at minus 40 dB per decade. We proved that particular behavior. And everybody remember what a decade was, right? What's a decade? Anybody who is awake, what's a decade?
Sir, hello.
Yep, I'm here.
Well, I just, well, but you know, try my best to participate. What I would say is well, not too sure on what decade is 10 years, but I don't want to, as it relates to the body plot, would it be every 10 counts or every, well, in terms of the log scale, you know, it does go by 10, 100, 1,000.
Right.
So assuming
that is on what you call that. You're correct. On what you call that? A decade.
I'm not. I'm not sure.
Multiples of 10.
Okay, multiples of 10. Yeah.
Right. So as you said, 1 to 10 is a decade. 10 to 100 is a decade. 100 to 1,000 is a decade. So this band is 10 times that one.
Yeah.
This one is 10 times that one, and so on. So it is a way of showing in a fairly small space a very large response. If you were to do this linear, then you're not able to draw this out, right? So this was a shorthand for us. And the decibel per decade was the sort of unit that we use because we plot the body plots in log scales, right? Both the magnitude, which is in decibels, a log scale, and the frequency, which is in a log scale, but a power of 10, right? Okay, so remember that a decade is always a multiple of 10. So it will occur elsewhere as well. And anybody remember what an octave was? That's the other one you're likely to encounter. A decade was a multiple of 10, and an octave was?
So a multiple of 8.
No.
No? It's 16? No? Sorry.
Nope.
Oh gosh.
Okay, go and check that one because the octaves occur. None of you all do music? None of you all play any instrument or have done anything with music? Octaves occur in that, right?
Yes, sir. Well, octave is 8 notes, yeah?
But in terms of you cover 8 notes, but the frequency from the beginning to the end,
right,
over the octave is what? What has happened to the frequency?
Okay, I'm not too sure.
Right, it doubles. Right?
It doubles, right.
So a decade is a multiple of 10, an octave is a multiple of 2. Right?
Okay.
So, all right. So if you plot this now, as we have it here, so when omega is much less than naught, or if we have a corner frequency here, you could also say omega much less than omega 0, right? The response is this flat 20 log A. And when it is much greater than omega 0 and approaches infinity, right? This part here is sloping at minus 40 dB per decade. Normally, when we do our Bode plots, you remember what the approach was? That you plot one line, you plot the other line, this was the corner frequency, so that the net, we approximated the frequency by straight lines, right? And that worked for us. We know that it doesn't change suddenly like that, but normally at the corner, it sort of slopes and so on. The systems that have damping, this bit changes quite a bit. If you were to just join the line here, this is ideal without a complex pole. And what happens at this point here varies significantly with the value of the damping factor. All right? And we're going to see now what exactly that sort of variation is. That is what this class or this lecture is supposed to be about. All right? So let's go on here a little bit. So this is the magnitude. And again, this really should have had a magnitude sign. This is the magnitude of the response, okay? We know that what the response, at least 2 parts of the response already. It's flat. Outside of the corner frequency here is flat, at 20 log A, whatever is. And as you go on past the corner frequency, it's dropping at minus 40 decibels per decade. But what happens in the middle? So if I give you something like this, an equation like this, and I ask you, well, what is the maximum value of this? Well, the maximum value of an expression looking like this would be when this is the minimum, right? So the smaller, whenever this hits its minimum, then A over that minimum will be the maximum value of H, the magnitude of Hj omega, right? So let's just call this bit inside here, right? We're going to call that d of omega, all right? It's been square rooted, but it doesn't really matter, right? So let's take the bit inside of here. If it's square rooted in the, whether it's a minimum or not, once you square root it, it gets even less, so it doesn't matter. So we let d of omega, there should be capital D here, this is more like a sigma, d of omega be this. And if you remember from your art maths, right, and you're going way back years now, if I give you an equation and tell you to find the minimum of the equation, what you did was to find the derivative and then see when the derivative was equal to 0. Remember that? So we're going to take the same approach here. So if d of omega is this expression here, right? To find out when this is a minimum, I'm going to have to find the derivative of this with respect to omega and set that equal to 0. Okay, so simple add maths, take the derivative and you get an expression like this. Right, you could double check the calculus, but simple, this is add maths, right? There's not even this CSEC stuff. Set that equal to 0. Now, and when you set that equal to 0, you will find that this is a 0 when omega is equal to this. Is equal to the corner frequency, whatever omega 0 is, by a factor here, right? Now notice something. This factor is only real if zeta now is between 0 and 1 over root 2, which is 0.707. All right? This is a little change because originally when we went back, and when you check your lecture, when you go back to the lecture, you're going to find out that originally when we had the response to the system, that zeta was restricted to between 0 and 1 in order for us not to have any oscillation when you go back and check the lecture, right? But as we're seeing now, in fact, when you're looking at the frequency response domain, zeta is further constrained to between 0 and 0.707, right? Fair enough? You're following the derivation, right? There's not big set of stuff. I've given you something, how to find the maximum. The maximum is when the denominators are minimum. How to find when the denominators are minimum. Take the derivative of the denominator, set it equal to 0 and solve. When you do that, you get a value here. So in other words, when omega is equal to some value, so usually the system has some value here, right? Depending on the type of system that you have, it's going to have a value of zeta. Depending on that value of zeta now, the system now is going to have a peak response at that frequency. All right? And again, usually because zeta is between 0 and 0.707, this factor here is relatively small, so that this usually, for many cases, is approximately equal to 1, right? So that omega r, is approximately equal to omega 0. When you plot it on a log scale, what you would get typically is like, just for argument's sake, if omega 0 was 1,000 hertz, you might find that the resonant, well, we call this a resonant frequency, omega r, that is where the peak frequency occurring, might be something at the order of 980, those kind of things. You can't show that on a log scale, right? You're plotting out decades inside of here, you could show 900, you could show 1,000, 980, those kind of things on a normal A4 page or a normal letter size page or something like that wouldn't be visible. So for the most of the cases, we kind of assume that omega r and omega 0 are about the same, right? So what's going to happen now is, first off, is that this function here, at some value omega r, this is going to get a maximum. So in other words, as you approach, remember, if we're saying that omega is approximately omega r, then we have this straight line here, we have this straight line response here, but as we get to the frequency omega 0 equal to omega r, the magnitude of h or j omega is going to increase. So this is going to do something like this and then come back down, right? What it does, this behavior depends on zeta. Okay, everybody following? Following the analysis on what we trying to derive? Yeah?
So far, so good.
Right? Okay. The derivation, as I said, that's simple mathematics here. You're just using some simple calculus. So the next thing now, so that we know that the behavior is going to do this, the last step that we want to know is to find out how large this rise at the resonant frequency is going to be. So what you do now, this is the magnitude of the response. So to get how big this gets at omega r, we need to substitute the value of omega r into this expression. And if you substitute it at omega equal to omega r, right? Omega r being this value here. So take this now, substitute it in the equation for the magnitude of h or j omega, right? Let's put this here, the magnitude of h or j omega. If you substitute it into that equation and you simplify it, you get now that the magnitude response is going to be looking like this. Again, it's a function of zeta, the damping. And because you're plotting it in decibels, you're going to have to take 20 log or whatever that is. Okay, so you could put in various values of zeta and let's see what happens. And then equally well when zeta is equal to 0.707. If zeta is equal to 0.707, then right at the point here, if you look at it, did I have a plot here? Right, there we go. Right, so as you increase it, we'll answer this in a little while, right? If zeta, as you increase, as you vary the values of zeta, notice what happens. As zeta gets smaller, let me go back down to here, right? This is zeta. As zeta gets smaller, notice the peak rises. Right, remember zeta is between 0.707 and 0. Right? It's not supposed to be 0. You could probably take off that sign here, because if we get to 0, then we have oscillation. We saw that from before. If zeta is like this case, 0.01, notice this is a normal, this is what it should have been doing. Right? This slope is minus 40 dB per decade, right? This is the 20 log A, right? So this particular example would have had A equal to 1, so this would have been 1 over something. Notice now, when zeta is close to 0, you get a very high peak. This is the peak rise here, when zeta is 0.01. As zeta gets bigger, the rise drops until eventually, when zeta is equal to 0.7, this is actually 0.707 here, you get this sort of response that are simple, a second order system with simple poles, the sort of response that you would normally get. Right, which is what we have done in some of the previous lectures here. So to answer the question, what about when zeta is 0.707? Right, as 1 over root 2. So 1 over root 2 squared would be what? 1 over root 2 squared would be a half, right? So you're coming back inside of here. You have A. This would be 1 minus a half. So you're back to the 1 over root 2 inside of here, and you could see what the actual value is and work it out from there. Right? It's a simple question. It's a simple answer. And at that point, the response simply does this. Right? Now that's half of the issue. Remember, the Bode plot has two things. It has a magnitude plot, and it also has a phase plot. Right? Everybody following what the magnitude response is therefore. Right? So if you were to, let me just go quickly back to the question that we were dealing with. Right? So here you're given, this is what the question is. You're given a stable system and you asked to calculate what the natural frequency is and what the system damping is. So if you're looking at this now, already you know from what we just did here, this straight line part, let me just zoom in a little bit, right? This straight line part here, this bit, right? This is 20 log A, right? This bit here is a straight line plot. This is decreasing at minus 40 dB per decade, right? Ideally, the system response should have been, you draw the two lines and you get the response looking, let me just see if I can draw a line here sideways to get something. Oh, wow, wow.
Excuse sir.
Yeah.
If can you just like just to give a little pointer as to how do you identify when it's minus 20 and minus 40? Is it just because the system is second order?
Exactly. Exactly. If you remember, if you go back to the first two lectures on the board plot, right? If you have a one over 1 plus, you remember you're substituting, so you have a 1 plus s. You substitute s equal to j omega, so you get it into the form 1 plus j omega over well, let's say some omega note inside of here. But when you convert this to a single order, will be when you convert this to logs, will just be 20 log of whatever this is. That decreases at 20 dB per decade. If you have squared, that will be 20 log of something squared, which is 40 log of whatever was inside of here. A cubed would be 60. A fourth order would be 80. Right? So because it's a second order system, anytime you see something with a square in it, you know that the frequency response is going to decrease at least 40 dB per decade, some point in the response, right?
Yeah, yeah.
Okay?
Okay, yeah, understood. Thank you.
All right.
Yes.
Right. So if you just plot this, what we have here, so you extend the straight line for this, it should, you're getting, it's hard for me to draw this thing on this tablet. The tablet is kind of in a different direction. Yeah, I must be able to get this better. Hold on. So what I'm trying to do here, go back to the pen. Right. So we have this doing this, and we have this line extending this way, right? Under normal conditions, this is what the second order system would have been looking like. But because it's a second order system, because you're now given a response that has this sort of response to it, that there's a peak at this frequency here, right? You now know that this is a system that has damping, which is why the question is asking you, what is the damping factor for it? So to determine that now, first off, we know what 20 log A is here. We know the resonant peak frequency is this, whatever this is. So this is omega R. And we just saw that you could calculate this now. So this is the rise at resonance. Remember, this is in dB. Right? So you could go and you could read it off from here. So if 20 log of A, this is looking like what? What value that is? That intercept is what?
About 25, 26.
No, this is not as 10. So this is.
Oh, not that one. Sorry, I was looking at it on top. Okay, about 5. 4.
Right, right. So if 20 log A equal to 5, you could get what A is, right? And here, as you said, you're looking like about 25, 26. So take a reasonable estimate, 25. So MR in dB is 25 dB. You could calculate what the absolute value of R is, MR, right? So if that's the case, then we can go back . Oops, wrong slide here. Where's the slide? Yes. Right? So, you know, you could get A. You just got A. right, from the intercept. You got MR, you saw MR in dB was 25, right? So 20 log MR was 25, so you could calculate what MR is. So if you know A and you know MR, you're now in a position to calculate zeta, right? This is an equation here. When you look at the solutions, you'll see. So this is an equation in zeta squared. So you're going to get two values of zeta. You're going to get zeta 1 and zeta 2. One is going to be less than 0.707, and the other one is going to be somewhere in the region, either negative or greater than 0.707. Which one are you going to pick? Because of the response.
So it will be the one that is less than given the range, or zeta 1, or is less than.
Right? You're going to have to pick that one because that is the one that generates this kind of response here, this kind of behavior, right? If zeta is not in that range, then you would get the lower sort of response here. That is not what the question is asking you. They're giving you a response that has a peak. So if it has a peak, it means that zeta is somewhere between 0 and 0.707. So when you solve, you have MR, which you get from the graph. You have A, which you get from the graph. So you solve for zeta. This is a quadratic here, right? To get rid of the square root, you're going to have to square everybody and solve for zeta. You're going to get two values for zeta. One of them is going to be in that range. The other one is not. So you have to keep that in mind when you're answering the problem. When you look at the solution, you will see it as well too, but try it before. You're going to get a value, two values, and you're going to have to pick the correct one to go ahead. Because that now is going to tell you, answer the other part of the question, which is this. What is the resonant frequency? Yeah? And you could get that from there. Right. So the last part of the behavior that we have to look at, there's one part is that the magnitude response, the both plot has a phase response. So we take the same sort of approach here. If I give you a complex number, right, which is, go back here a little bit. If I give you a complex number, 1 over A plus J B, right? The angle of that, of course, is the arctan of, well, let me hear you. What's the argument of that? See, another little bit of CSEC stuff here, right? Complex numbers, right? Is the arctan or the inverse tan of the imaginary part, the imaginary coefficient over the real coefficient. Because it's one, that would have been if it's A plus JB, because it's 1 over A plus JB, right? The argument of that is minus the arctan of the imaginary part over the real part, right? Yeah, simple complex numbers. This is the angle of the phase angle of the frequency response. So again, we do the same thing. If omega gets to 0, or omega is much less than omega naught, this goes to 0 so that the arctan of that is 0 degrees. At omega equal to omega 0, right? This now becomes 1 so that you have tan of something over 0, which is infinity. So that the inverse angle of that is minus 90. And then as omega gets much bigger than omega 0, all right, this continues along the way until it comes, because this now is increasing at a bigger rate than this. eventually, as omega gets very large, this goes back down to 0. So that you now back down, you started at 0, you're going to minus 90, and it goes back around to you get a minus inside of there. So the actual angle now is minus 180. Right? So if you were to plot that, the phase angle plot would be 0. This is omega naught here. So less than omega naught, it's a 0 degrees, minus 90, minus 180. At the resonant frequency, right, it becomes 180, sorry, minus 90. And then as you get much bigger than omega 0, it goes to minus 180. So the straight line plot would actually be looking like this. This is the phase plot. The actual behavior of it, of course, nothing changes suddenly. The actual behavior would be something like this. So it passes through 90 and then it heads on to minus 180. All right? How fast it does this is strictly a function, again, of the damping function, right? And if you were to plot it, you would see like here, right? When the damping function is very close to 0, you get a very sharp transition from 0 degrees to minus 180. That's the turquoise line here, which corresponds to the high peak. When it's close to 0.707, which is a limit, you get a gradual roll off in the frequency, and you also get a gradual change from 0 degrees to minus 180, which is like your normal second order function. All right? And this point here, of course, is easy to read. This is at omega equal to omega 0. All right? So by looking at this, if you're given the figure here, you could either read it off from the upper graph or look exactly at 90 degrees and read off what the frequency is. So for this particular example, omega naught is equal to 10 radians. No, 10 to the naught is 1, sorry. 1 radian per second, right? 10 to the naught. So that's 1 radian per second. So if omega naught is 1, all right, so this is peaking at omega naught. And if you notice this zeta, this is what I was telling you. If zeta is 0.01 and you plug it back inside of here, you can see this is 1 radian per second from that graph. Zeta is 0.01. So this is going to be very, very small. So you're going to see that omega r is almost the same as omega 0. Yeah, that was the point I was trying, that we're trying to make. And if you go back now to the question, where was the question? This one. Right? So you're given everything now, right? You calculate from here. Now, if you go to the phase plot, you could see. So what is omega 0 for this? If I look at this, this is 10 here. This is 20. This is 30, 40, 50, 60, 70, 80, 90, 100. Now, what's our log scale decimal? Oh, sorry, a decade scale. So this point here will be 10, 20. So omega naught is 30. Look at the units here, 30 radians per second. So if omega naught is 30 radians per second, you could calculate zeta from this. Remember, you know MR, and you know A. So you go back to the equation and you get the two values of zeta. You pick the one that is between 0 and 0.707. And then now you could go, if omega naught is that, omega r is equal to omega naught square root of 1 minus 2 zeta squared. I think it is, right? And you can put that in inside of here and you will see what the actual resonant frequency is, right? So this one didn't even ask you that. It is asking you basically to look and understand what the diagram is. So what is the system natural frequency here? Straight off. You look at the bottom plot here where it crosses 90. So that's 30. So you have that answer already, that's 30. So that's easy marks here. And the system damping is a little more complex. So you're probably getting 4 marks here and 6 marks for this question. So just by looking at the diagram, you have the answer. Omega naught is 4, is 30, right? There are 4 marks here. The system damping, MR, you need to get MR from this, you need to get A. And then you go and you go back to, which slide it is? This, right? You go back to this formula here. You substitute A, you substitute MR, you solve for zeta. You're going to get the two values here. And because the response has a peak in it, you have to pick the one that is between 0 and 0.707. If you get two values, and one is close to 0, and the other one is close to 0.707, both of them are legitimate values. And this is where your knowledge of the system is supposed to take place, right? You notice that as zeta gets close to 0, you get a high peak. As it gets close to 0.707, the peak disappears. So if you're given a figure and you calculate the two values, because this is a quadratic, you're going to have to choose now which one it is. And of course, the answer for that is the one that is close to 0. All right? Okay, so let's just tidy up that here. Right, so be able to, in fact, just let me get the one that I was writing upon. That is this. Right, so you're now able to get the to get the marks. Well, first off, if you solve on you get the two values and you pick the wrong one. If you get A for this, you get A, M, R, right? So you get 1 mark for A, you get 1 mark for calculating MR. Of course, you need to convert from the decibel scale here into the normal number scale. If you use MR as 25, you're getting it wrong. Okay, and then from this now, you're going to get two values of zeta, and I expect you to be able to know that the value, because of this sort of graph, because you're seeing that you have a peak here, that zeta is somewhere closer to 0. So when you solve it, I expect you to be able to pick that out, and then you get the rest of the marks for that. So questions. See, very straightforward, right? And again, there's nothing in here, no terrors, no hidden surprises inside of here. It's very straightforward. You're given something. So the sort of things I could give you would be a question like this. If you check the past papers that we have, you could get this kind of question, or I could give you the transfer function, right? So I could give you a second order transfer function, 5 over s squared plus 50s plus 100 for argument's sake, right? And tell you, draw the Bode plot for that, right? Once you do this kind of thing and you find out that the roots are complex, right? Then from this, you're going to have to find A, you're going to have to find MR, and you're going to have to find omega naught, right? And then you plot this kind of figure for me. It's a straight line plot, and you have that. So you plot in the magnitude response, which will be the 20 log H J omega in decibels. So 20 log A would be this. Omega naught would be here, right? You will plot that is decreasing at minus 40. And then right here, you put a little line right here. And this is supposed to be MR. And then you have to tell me on the axis here what MR in decibels is. And then the phase plot right below, remember that it goes from 0 to minus 180. And the actual, it passes through minus 90. This is not minus 180. It passes through minus 90 at omega 0. Right? So this is omega 0 here. Right? Just like this kind of figure here. I don't expect you to give me this accuracy. You draw the two lines and give me a line showing me how high the resonant frequency is. So there are two types of ways I can ask the same question. Okay, and you will see it in the past paper questions that I've done it both ways. Okay, so questions. Everybody all right?
Yes, everything good.
Right. Yeah, like the Mike Tyson thing, right? Everything good until they get hit. But right? This thing when everybody had a plan until they get hit. Right. So all right. So listen to it, look over the notes again, try the question without looking at the answer, and then see what the answer says, and let me know. Right. The one other topic now, I saw somebody had put on the Google sheet that they wanted a little more discussion on Fourier series and transform, but you have to be specific because we did that. One of the earlier lectures in reviewing this was on those topics, but so you have to tell me specifically what the issue is. If you're talking about calculus and doing the integrals or something like that, that is a different story. All right. But in terms of understanding the material and so on, let me know. Right. We have about 6, if nothing else comes up, we actually have 6 sessions together left. So we still have a bit of time. The one topic I want to review again, and I'll do that on Monday, please God, is convolution. Just to talk a little bit about it in general. And then, but in the meantime, your job now is really to review the past paper questions and to see where you get stuck, or to see if you're not getting the answer I have, or to see the answers that the handwritten solutions there that I have put up, if there are any errors in them. Occasionally there are errors that I pick up as I'm doing it, as I'm correcting the scripts. I make the correction, but sometimes I do update the solutions that I have online. All right. Okay, so well, like I say, it's in your court now. We have one topic that I will pick, which is convolution now, and really that's it for everything. So you are it's your call now. You have to try things and see where you're getting stuck and so on, and then I'll decide after the convolution how we're going to work out the remaining classes in terms of how we're approaching it. Okay. All right, so if that's it, I'll stop there.